Now we turn to insertion. Let's see how to add a new node to a doubly linked list, first at the front and then at the end. Let's add a new node at the front of the list. In a doubly linked list, this takes 4 writes. The new node sets both of its own links first, prev to null and next to the old head. Then the old front node points back at it, and last of all, head moves. Let's look at the before and after pictures. This is the list before. Head holds 3000 and it points at node 10. Node 10's next field points at node 20. Node 10's prev field is null because it is the first node right now. This is the list after. We made a new node 5 at 4000, shown in green. Node 5's next field points at node 10. Node 10's prev field now points back at node 5. And head has moved to 4000, so node 5 is the new front. Let's predict first. 4 writes make this insert. We set X arrow prev becomes null. We set X arrow next becomes head. We set head arrow prev becomes X. And we set head becomes X. Which one must run last? And what breaks if head becomes X runs first? Pause and think. Now the answer. We must move head last. If head becomes X runs first, the old front node is lost. The list already names the new node, so X arrow next and head arrow prev can no longer reach the node that used to be first. So the key idea is that order matters now for 4 writes. Set the new nodes on prev and next, and the old front node's prev before you move head. If you reverse that last step, head already names the new node before its links exist. 4 pointer writes, and the whole thing is big O of 1. This is insert at the front. Written in C, this first half sets up the new node. We call malloc to make a node, and we store its address in X if malloc fails. X is null, and we return at once and leave the list unchanged. Then we set X arrow data to the new value K. We set X arrow prev to null, because the new node will be first, so nothing comes before it. And we set X arrow next to the old head, so the new node points forward at the old front node. Notice the order. The new nodes on 2 links go first. Here is the second half. Now we fix the neighbor, then move the handle. If head is not null, the list already had a first node, so we set that old head's prev to exit now points back at our new node. Else the list was empty, and then X is the only node, so it is the tail as well, and we set tail to X. Finally, we set head to X, so the new node becomes the front. Moving head is the last write, exactly as we predicted. Let's look at the cost. Insert at the front is big O of 1. It is just 4 pointer writes. Nothing is walked and nothing is shifted. It is the same cost class as chapter 4. We just do 2 more writes to keep both prev links correct. Now let's add a new node at the end of the list. In chapter 4, this cost big O of n because we had to walk all the way to the last node. Here we keep a tail pointer which always points at the last node. Because of that cached tail, append is big O of 1. There is no walk at all. Let's do it 1 write at a time. Step 1. We run X becomes malloc, which gives us a node at 4000 holding the value 40. It is not linked to anything yet. Its prev and next field still hold garbage, shown here as question marks. Step 2. We set the new nodes on 2 links first. We set X arrow next to null because it will be the last node. And we set X arrow prev to tail. So node 40 now points back at the old last node, but tail itself has not moved and the old last node does not point at us yet. Step 3. Now the neighbor. We set tail arrow next to X so the old last node, node 30, points forward at node 40. Both directions are linked now, but tail still holds 2000. Step 4. We run tail becomes X tail now holds 4000, so it points at node 40. The node is appended and the whole thing is big O of 1. There was no walk. Let's predict first. Say insert font is called once on an empty list, where head and tail are both null. What are head and tail afterward? The answer, both head and tail point at the single new node. Though as the list empty branch sets tail to X inside insert front, and the same branch appears symmetrically in insert end, where it sets head to X. This is insert at the end. Whitman see it is the mirror image of insert at the front. In this first half we set up the new node. We call malloc and store the address in X if malloc fails. We return and leave the list unchanged. We set X arrow data to the new value K. We set X arrow next to null, because the new node will be last, so nothing comes after it. And we set X arrow prev to the old tail, so the new node points back at the old last node. Again, the new nodes on two links go first. Here is the second half. If tail is not null, the list already had a last node, so we set that old tails next to X, it now points forward at our new node. Else the list was empty, and then X is the only node, so it is the head as well, and we set head to X finally, we set tail to X, so the new node becomes the last node. Let's look at the cost. Insert at the end with a tail pointer is big O of 1. There is no walk. Compare this to chapter 4's singly list insert at the end, which was big O of n, because it had no cached tail pointer.